Welcome to our last round here. Our guest is Wolle. He's professor for data science at the University of Oldenburg and is data science advisor at Techcamp.
Yeah.
He will tell us a bit about probabilistic data. I know I'm saying wrong, but Wolle will tell us what it's all about and what it is. Stage is yours.
So thanks for the introduction, and hi everybody. I'm Wolle, and today I'm excited to be stirring up the hype for probabilistic data structures. So the talk today is titled Most of the Time It Works Every Time, and I'm trying to basically get you hyped and get you into the right mindset for using probabilistic data structures. So ideally by the end of this talk you have an idea what probabilistic data structures are and why you should actually use them more often. So just as a bit of background on myself, I'm a professor for data science, but I'm actually just a data engineer. Please don't tell anybody. So I'm always telling everybody that I'm doing data engineering for data science, and this is kind of my research history. So I started at the University of Hamburg more than a decade ago, which makes me really feel old. And I did my PhD there in the databases group. So, data was basically from the beginning the overarching theme here. And I actually started trying to benchmark databases and find out what, makes a good database, what the different qualities of database systems are, and how you can compare them. And that quickly led me to the conclusion that traditional databases are kind of lame when you're working with big data. So I dived into NoSQL stores and then tried to get basically a grasp on the system space there. And then I found out that it's actually also pretty lame what NoSQL systems can do, because if you are building web applications and you want to, for example, implement stuff where people interact with one another, then you actually need something that does continuous processing, and you need like live updates and update feeds and things like that. And basically no system at the time provided support for this kind of thing. And therefore I, in my PhD thesis, was very much concerned with building systems that have scalable data, like NoSQL capabilities, but could also give you like live updates on stuff that happens in your database. So I kind of connected NoSQL systems and stream processing systems, and then built like 5 years at a time a scalable real-time database system. And that was also where I joined the company Backend, because they needed such a thing. That's a web company. They're trying to basically make the web faster. And at the time, we thought having a real-time database would really change the game. Turned out that wasn't the case. So then I was at the company, and my baby was actually not being used in the way that we thought it would be. So I pivoted to web analytics. So I then built kind of a scalable tracking infrastructure to monitor web performance on websites, and became head of data engineering there. And then eventually in 2022, I realized that I am kind of the research guy and really like to give lectures, which is also why I'm here today. And I then joined the University of Oldenburg. And there I'm currently researching different things, also in the realm of data quality or hands-free coding. I think last year I was here talking about hands-free coding, so you may have seen me there already. But what you may be noticing here is I'm very much a data guy. And in basically all stages of my academic career, I have been using probabilistic data structures on and off. And the core technology at Backend is basically also reliant on Bloom filters, which is a probabilistic data structure that we'll see later in this talk. And I noticed at the university that many students don't have an idea what that actually is and why you would be interested in probabilistic data structures. And that's why today I thought it would be cool to have kind of a mini lecture on probabilistic data structures. And we have mainly 3 parts here. So the first one is we'll start with the, let's say, most awesome probabilistic data structure I know, which is skip lists, because last year I stumbled upon them and I was shocked that I hadn't ever used them before. So I will tell you what a skip list is, why it's cool, and what the basic idea behind skip lists is. And when we have basically talked about the idea, we will realize that it doesn't work in practice. And that's why you need to introduce the probabilistic element which is kind of the awesome part about the skip list implementations that you can actually use today. And we'll talk about what the probabilistic, so the chance, the luck element is, why it makes skip lists efficient, and then also how you can analyze complexity to understand that it's, even though we have kind of random stuff happening, it's still pretty reliable and gives you great performance in basically every case. And then in the end, we'll also talk about other probabilistic data structures that solve different problems, and we'll talk about what the trade-offs in those data structures are and when you would use what kind of data structure basically. So I don't assume much prior knowledge, I think, but I'm also not sure. So here's a list of stuff that helps you if you have heard it already. So if you have a rough understanding of data structures from basic programming courses, that's helpful. So like the basic list types, for example, or what a hash map is, that there are things like self-balancing trees and so on. Then I also think that most of you should know, there are algorithms and you can analyze what their performance is, like are they logarithmic or quadratic or linear in time or space complexity, things like that. And there are many applications where you need simple things like a sorted list, or a hash set or stuff like that. And I assume most of you have built things like this or have even at least touched those application cases, so that you can imagine cases where it's reasonable and helpful to have an efficient list. And by the end of this talk, this is kind of the learning goal. Everybody here will hopefully have an idea of what probabilistic data structures are in general, and specifically what skip lists are, why coin flipping is a thing in that context, and also you have a rough understanding of what Bloom filters or count-min sketches are and what the inherent trade-offs and use cases are there. So starting with skip lists, the basic motivation for having a skip list at all basically is that sometimes you need to sort a list. And it can be, so here at the bottom you see the list, and you always, when I say list, I mean something like a sorted key value pair. So imagine you have a user list, and every user has like a primary key, so some number as an identifier, and then a name. For example, when you've used Redis, the sorted list or sorted set implementation uses skip lists internally. Or when you are using Discord, the user list on Discord servers also uses a skip list. And when you do data science stuff, sometimes you just need to implement something, and I don't know, you're maybe maintaining a list of medians, in a large sliding window, could also be helpful to make this happen with a skip list, and for the rest of the presentation, at least for the skip list part, we're only showing the keys here, because if I had shown the usernames everywhere, then the slide would be overfull. So just whenever you see something like a node with a number, just know that this is only the key, and there's a value attached with some useful information for your application. And maybe just think of the Discord server where you have users and you want to maintain the user list in sorted fashion. You would start with a standard list maybe for your prototype, but once you scale up, this isn't really smart. And the question is, why shouldn't you just use something like a sorted list, or maybe also a sorted like a linked list or array list? The problem here is that these basic list implementations are easy to understand and implement, but they are kind of lame in different aspects. So with the sorted list, the problem is that searching things in that list is very slow. You just have individual nodes and they are pointed like chained together. So you have to start at the head and then go through the list until you find your item, which is lame. However, once you've found the item that you're looking for, updates are very easy and very fast, because you can just insert new nodes and then wire up new pointers. So there's something good and something bad here. And the other way around, with sorted array lists, you can have actually really efficient search because we have point lookups in those array buckets. We can just here, for example, we're looking for the 6, so we just check the middle bucket there, and then we know, okay, that's 17, so it's too big. But since the list is sorted and since we have point lookups, we can just check the middle, like between the first and the 17 there. And since we can just jump here and always basically cut our search space in half by jumping to the next middle of the let's say portion of the list where we're still looking for, the search complexity here is logarithmic, so that's awesome. But updating in turn is ultra lame, because inserting a new item means we have to shift everything following the item position around, and this is super expensive if you're changing stuff like in the front part here. So summing up, the cool thing about standard lists is that sorted lists, linked lists, give you fast updates, and array lists give you binary search, which is cool for logarithmic search complexity. But can't we have a list that gives us both? Yes, the thing is we can, and that's skip lists. And that's now the beauty part. Basically, what's the idea behind skip lists? So we actually want a linked list because that's good for updates, but we need shortcuts so that we have this logarithmic search complexity. And the idea with skip lists is that we just introduce, let's say, express lanes to introduce shortcuts and just skip items in the list. So you can imagine you have, you see it at the bottom there, the normal lane, which is just the standard linked list. But since we need to traverse a list when it's a linked list to find things, we don't want to traverse every item one by one, but we want to skip things. So we introduce an additional level and say, okay, the level is just illustrated by making the nodes bigger. Actually, as you can see here, we still only have one value or one key, but we have additional pointers here. So every time I'm talking about an additional level or promoting a node to the next level, that just means we introduce new pointers from that node to some skip node later. And the idea is that, normal lane has all the nodes, the second lane has only every second node, the next lane then again has only every second node from the lane before. So here we have always like one node, and then we skip 3 nodes, and again we have a node here. And you just do that until you only have one node left. That means we basically have kind of this logarithmic structure where we can, depending on the lane, skip very many nodes. Okay, now just imagine this is the list structure that we have. How do we find stuff? Imagine we want to find the 19, and I really hope that you can see the numbers there. What we do is we start at the top, so at the highest lane, which is the ultra express lane, because you see we actually only have a single node here, which is, like the predecessor is the head and the successor is the tail. You start at that level here at the head position, and then you just always advance on the lane that you're currently at until the next step would overshoot your goal. Because here we want to find the 19. That means we can't even go a single step because the next step would be 21. So we go down immediately. Then we're at the next express lane here and advance until we would overshoot. So we go to the 9, can't advance to 21, so we go down again. Then we advance until we are at 17 here. And then again we would overshoot, so we go down again. And then we reach 19. And the thing is, by doing this, we know that eventually we will either encounter the node on some lane, or we will go down to the normal lane and we'll reach the successor. So we know that the node isn't there. And then we're also done. So we either have a success or a failure, but we will find the node, and we will find it by skipping nodes on our way down, which is a good thing. And if you think about how long this can take, we know that we have log n levels in our list, and we know that since we cut the search space on every level in half, every time we will never visit more than 2 nodes per level. And that means we have logarithmic time complexity because there cannot be any search path that has more than 2 log n nodes, which is super awesome, because now we have a linked list with logarithmic search complexity. So it's kind of as awesome as an array list. And another cool thing is that we even have linear space complexity because we can't have more than 2 endpointers. Now you may say, okay, how is that? The thinking here is basically that you could build a sum of all the pointers in your list, and then you would say, okay, if we go through all the lanes, we have n nodes on the first lane because that's the actual normal linked list, and then we have n half nodes on the next, and n quarter on the next, and so on and so forth. So that here would be the sum for getting all the pointers in your entire list. And if you're a mathy guy or girl, you may realize that this is a series that you can simplify and the result is 2n. So the entire thing here, bless you, converges to 2n. And that means we have logarithmic search, time complexity, and linear space complexity. Life is good, but what about updates? Yeah, another thing is some updates are awesome, like just, for example, updating a username. You search the node, then you replace the value. That's basically like search. But then there's also insert and update operations, and they also can be efficient. So for example, here, if we think about inserting something like 27, super easy, because we could just add the node. However, sometimes updates are also really bad. For example, imagine you want to insert something like the 20. What you need to do is you need to put it here, but our structure requires that the next node here has like level 4. Yeah, dang, there's a level 4 node already. So we need to change this node and make it like level 1 node, and then the next one should also be promoted to level 2. You get the picture. This is super ugly because we basically have to chuck out all the stuff here and then replace it with new stuff. And this is some heavy rewiring. You basically have to touch the entire thing. This is like the lame part of array and linked lists combined. So we don't want this, but how do we solve the problem here? Because the issue is everything is cool, but some updates are super ugly and we can't really like make them efficient. And the problem is the perfect skip list structure. That's the core issue here, because our perfect skip list is just not maintainable in efficient manner. And the idea to basically solve this problem is that our current requirement of having exactly half of all nodes being promoted from one level to the next kind of relaxed. We say, okay, exactly half nodes, not necessarily. Let's say it's kind of an on average thing. So the perfect skip list that you would actually want isn't the one that you're using in practice. In practice, we're kind of using like the best effort skip list here. So we just build our skip list, and I'll explain in a minute how we do that in such a way that most of the time the structure is kind of optimal, but sometimes it's really bad. Could happen. But by accepting this, we can basically insert nodes even if they violate the perfect idea of the skip list. And the thing is, expected performance will still be the same, but sometimes we can get bad performance if we're really unlucky. And the core component here for deciding what kind of structure our linked list ends up with is basically that we don't have this deterministic rule for promoting nodes to the next level depending on how many, like here we say, okay, you have level 1, then level 2, then level 3, and so on. But we rather say we just flip a coin. So you insert a node, and the level on which, or the pointers that you wire this node up with is basically determined by some value p, which is 50% in the standard case for lectures, but you could also modify that. So for example, you're flipping the coin, and if it's heads, then your node will get promoted to the next level. Then you flip again until you get tails. And once you get tails, then you will just stop promoting your node. Okay, so now, we have kind of the idea of a skip list. We have kind of the expected performance of a skip list. Let's see how that changes the update procedure, because you have to take, let's say, special precautions here when you do things with your skip list, because we need to maintain the order to actually use it in practice. So let's assume we want to delete a node in the list here at the bottom, like the 17. What we do is we perform normal search, of our node, and we go all the way down until we find it on the normal lane here. And the special thing that we do now is we keep track of all the predecessor nodes that we visit on all the different levels. So again, we start here at the top level and say, okay, can we advance? Yes, we can, because here the first node is the 6, so we wouldn't overshoot. We go until here, and then we can advance. So we go down one step, and then on the next level here, and again, next step will overshoot, so we go down again, and then we reach the node 9 here, and now, watch out, we could reach node 17 already, but we need to get all the predecessors, so we go down one level regardless until we have the predecessor node of the node that we want to delete on every level, and that's basically here the vector that we stored. When we then delete the node 17, there's a hole in our skip list, and that's why we need to remember all the different predecessor nodes, because now we can actually, that's the red arrows there, we can now wire up the nodes that actually have the hole in the skip list, linked list structure here. So okay, now deleting is pretty efficient because we just accept that now we have maybe a hole in our skip list which kind of disturbs the overview, the overall view here. What about inserts? Now, how does that work? It's basically the same. So again, we would start with the search and then find the position of our node on the normal lane. So, we don't need to do this in detail. Again, we remember the predecessors, also like on the last slide, and now we have the position where we want to insert our node. So we start flipping a coin. Obviously we're on the first level either way because we need to insert every node on the normal lane. Then we flip a coin and we get heads. So we also say, hey, it's promoted to level 2. Maybe we get another heads. And then we say, okay, it's promoted to level 3. And eventually we will either reach the topmost level or we will get tails. And then we know, okay, this is our node and we need to insert it here. And now we remembered all the predecessor nodes, so we know that if you insert stuff here on the first lane, like on the normal lane, predecessor is 12. So you go to the node 12, check what the successor of node 12 was, which is 19, and then you update the predecessor, the successor of 12, so you wire it up with the 17, and then you set the old successor of 12 to the successor of 17. And you do that on every level, and then you basically, and that's the cool thing here, we just touch the immediate predecessor and immediate successor nodes of the node that we're inserting here. So the insert is still pretty cheap, because we have the logarithmic search to find the position, and then we have the more or less constant time update for actually rewiring things. So now I mentioned that we have the option of configuring the p-value here, and typically you don't take just some value like the fair coin thing, but you would maybe tune this to your specific requirements. So here's a smart looking table that gives you all the information you may or may not need. What you see is that with 50% promotion probability, you can, here are the formulas for computing things, for example, the time complexity and the space complexity. And here the interesting part is basically this here, because it's divided by the, here I just made examples for list size 128, and here it's normalized by the number so that we have some factor to do relative comparisons of the p probability here. And what you see is that for 50-50, this is our baseline, so time complexity would be 1. Then if you take, I don't know exactly why, but if you take 1 divided by e, it's getting slightly better, but generally the trend is, if you reduce p, you see that time complexity goes up and space complexity goes down. That means, intuitively speaking, reducing or shifting the promotion probability down, means that you have a higher likelihood that your node stays on a low lane. And that just means you have fewer pointers. That's why space complexity goes down, because we store less pointers, and time complexity obviously goes up because having fewer pointers means that we have to do the sequential traversal thing on the normal lane and the other lanes more often. So basically decreasing p-value means you can get better storage efficiency, but you also get slower searches. And now the question is, what exactly does slower searches mean? Because I said, on average, we're still with a perfect skip list, but what does that mean? Because I think the official term is kind of, you get logarithmic complexity with high probability. And this sounds super vague, because what does that mean? It basically means, okay, with some probability, search might be slow, and with some probability, like worst case, we just have a linked list. So what are the odds? And again, there's a smart thing to look at here. So what you see here is basically a chart that gives you on the x-axis the expected search costs. So that's basically, expected is the average, so what you would get in a perfect skip list, so logarithmic search time. And here you have factor 1, so that's basically the perfect case. Then 2 means our search is taking twice as long as it should be in the best case, in the skip list case, and 3 times 3 here means it's 3 times as slow as you would expect in a perfect skip list. And on the y-axis here, you see it's logarithmic. Here you have probabilities, and the different colors of the lines basically is for different p-values. But I think it doesn't really matter what kind of p-value you are using. What you see is just that the odds are pretty low. So just to explain it, like this line, what you see there, like getting a 3 times slower search than expected with a list of, I don't know what this thing here is, I think 4,000 elements and p 25%. It's like you go to a green field, pick a clover, and it has 4 leaves on first try. Or here you have the chance of buying a lottery ticket and winning. And here at the bottom, you have the chance of, you have a skip list with 4,096 items and I think p 50% or what, I can't really see it here, and your search is taking 3 times longer than expected. So this chance is super abysmally small. It doesn't happen in practice. So what the takeaway is here with a high probability performance thing is, if you have a skip list that is rather short, then there is a very, 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 very small chance that you end up with a pretty bad search speed. But the thing is, the longer your list gets, the less likely this becomes. So if you have a list with 1 billion items, you have rather bits flipping than having a really, really, really bad search performance. And on search lists that are really, really short, it doesn't really matter. So the with high probability part means that actually performance is pretty nice. And if you start worrying about your skip list degrading because of bad luck, then you should also be worrying about, as I said, bits flipping and power outages and stuff like that. Now, if you are a computer science geek, you may be wondering, okay, sounds nice, but logarithmic time complexity and linear space complexity, for sorting stuff, we have trees for that. So why on earth should you use a skip list? So let's ask the man, Bill Pew Pew, the skip list inventor. And what he says in his skip list paper is, okay, honestly, guys, from a theoretical point of view, there's no need for skip lists. So he says it himself, actually you don't need this, because balanced trees can do everything that can be done with skip lists, and they also have good worst case time bounds, and skip lists don't have that. So why are we talking about this? And I think there are 2 good reasons. The first one is, skip lists are actually easy to build. So it's data structure, you can implement this yourself, and you understand what's going on. And if any of you have ever seen like industry-grade implementations of tree indexes, it's super complex. Like people have poured hundreds of woman years into implementing these database indexes and tree structures because they are really complex. And these rebalancing operations really make it hard to understand what's going on. You don't have that with skip lists, and also they are super robust, because with trees there are sequences in which you can insert data into your data structure, and they just make it so that performance isn't optimal. And with skip lists we don't have that, because we have this p-value, and it just is a random element there. And the obvious advantage of using trees is that they are really predictable, because the complexity bounds there are not probabilistic, they are actually worst case. and they are super efficient by constant factors simply because the skip list always has a branching factor of 2 and trees have like branching factors of 100 or whatever, and this actually makes the trees way shallower than skip lists could ever be built. So honestly, if you're really serious about performance, you would probably use a tree, but if you are maybe implementing something and you don't want to have the extra complexity, you could just use skip lists and still understand what's going on. And this is basically the skip list part. So if this were a real lecture, then we'd probably also talk about variations of skip lists. So we could talk about the impact of choosing different p-values, or actually do a real complexity analysis with more mathy stuff here. We could maybe in a course, make a performance shootout, like everybody writes their own skip list, and we try to see which performs best, stuff like that. And we could also talk about different probabilistic data structures. And while I was doing this slide, and that's why we have this talk actually, I thought, yeah, why don't we do this? Because I think now you have kind of, I hope, an appreciation of why skip lists are cool, but there are also other data structures that are also cool. So let's throw in a few slides on them as well. So another probabilistic data structure that is really close to my heart is the Bloom filter. And that's because we have used that at backend and still use that at backend heavily. And the idea, once going back to this user list example, is that maybe we have a very large user base, and if you want to query this user list, basically going to the list every time is kind of expensive. Imagine you have maybe a very, very popular app, and now you're trying to check whether a given username is still available. Then the app server doesn't or shouldn't access the database for every new registration, because accessing the database all the time for this is kind of lame. There should be a better way. And the idea of a Bloom filter is something that can actually solve this. So imagine you create a Bloom filter for your user base, and that means we have some hash function that compresses your user base list, so your username list, into a bit array. And here the example is the hash function is just we take the first letter of the name, and then we have like 1 bit for every possible result, and that's what you see here. So the Bloom filter of the list on the left would be what you see there, and the T there just means true for Boolean. We just have the information. Is there somebody with a name that starts with an A? Is there somebody with a name that starts with a B? And so on and so forth. And the way to use this data structure would basically be, instead of asking the database every time for every registration, the application server has this Bloom filter and just checks the Bloom filter first, and only if the Bloom filter says, yeah, maybe there's somebody with the same starting letter, then you ask the database. So you basically, for example, you're registering a new name, then you compute the hash for that name, you check the Bloom filter, and if the Bloom filter says no, there's nobody like this, then you don't have to ask the database, because there's no there's no way in hell that this username is already taken. So example, Zach is registering, and you just check the Bloom filter and see, okay, nobody with this hash is in the Bloom filter, because this bit isn't set. So we can safely say, yeah, Zach, go on, your name is free. Awesome. If Wu is checking the same, then we would say, hey, W, there might be somebody, in this case, Wolle and Will, so we need to check the database, but we don't have to check the database every time. Now, obviously, it seems kind of simple here, but you would typically take more bits, you would take more complex hash functions, and also you would take more than one hash function. The trade-off here would be that you have memory efficiency, because it's obviously a very compressed data structure here, and on the other side, you get false positives, because in this example, you see that you can't really distinguish between Will and Wolle and Wu. So if the Bloom filter says, yeah, Woo, your hash is in the Bloom filter, it doesn't mean that Woo is in the username set. It just means that there might be somebody like this, and it's a hash collision. And to avoid this and make the possibility of hash collisions smaller, you actually have to increase the number of bits and hash functions. Christine, könntest du einmal Strom anschließen? Sorry, I'm not sure whether my power will suffice, so we'll wire the notebook up while on stage. As I say, the tuning parameters are the number of bits and the number of hash functions, and if you get hash collisions, this only produces false positives. That means if you check the Bloom filter and it says no, nobody like this is in your Bloom filter, then you're like 100% safe to use that information. And as I said, this is something that we use in SpeedKit heavily. So here are just the thank you. Here just a few references, like a presentation where we explain the technology, and also papers on the core data structure, which is called a cache sketch, and also on the SpeedKit technology in itself. And in a nutshell, how we use this at backend is there's a Bloom filter for every user that will visit the website, and this Bloom filter is kept up to date by our infrastructure. So every 30 seconds or so, your device checks a very small, like 2 kilobyte or I don't know how many kilobyte Bloom filter to see what resources have changed, and then the client knows what caches can actually be used or what needs to be reloaded from the website. So imagine something like you have a search result in your web store, or something like response from some JSON endpoint. You typically can't cache stuff like this in your browser, because your browser cache is TTL based. So you have to decide for how long the data is valid. And with SpeedKit, you can actually cache stuff and say, okay, this response is valid for 1 day. And if it changes, regardless, the Bloom filter lookup basically tells you, hey, your resource has become stale, better be safe and reload it again. So we don't actually store usernames there, but invalidated or updated resources that we use for caching. But this is kind of the magic why we can cache more than any other web acceleration approach here. And another approach, like also a probabilistic data structure here, is the count min sketch. And there again, imagine you have this application server and it doesn't want to check what username is taken, but rather it wants to check how active the users are. So then we would have a structure like this one. This time we don't have bit arrays, but counter arrays. So now we don't have true, false, but real numbers there for every letter. And here the examples are the first function here basically takes the first letter of the name, and the second function, like the bottom one, it takes the last name of your, the last letter of your name. And the idea is that instead of counting the messages that every user sends, so having a counter per user, we just have a counter per hash function and per value basically. So here again, since our output values of the hash functions are letters, we have 26 columns and 2 hash functions. So for every name in the database, we have 2 counters there, and the idea is that we basically count the hashes instead of the users. And when you want to know how active has this user been, then you compute the hash functions for the user. Then you check the counter values in all the columns that are relevant, and then you take the minimum value. Because, sometimes, example, you have somebody like Fabi, and you want to handle that he just sent a new message. So then you compute the F and the I as the hash values. You go to the counters in your data structure and increment the number. And if you want to look something up, for example, my activity, you take the W and the E counters there, and you check the value. And obviously, like here, for example, Will and Wolle have a hash collision on the forename, and Jane and Wolle have a hash collision on the last name. So you don't really know, what you are seeing here, but you definitely know, if you're looking the counters up, hash collisions will only lead to additional increments, but never give you a too low value. You know, so the count min sketch also has like constant size, and if you tune the bits and the number of hash functions correctly here, you get a very low error rate, and you also know that the values that you retrieve for your user activity here is actually an upper bound. So you know that it's not less or like not lower than the value that you get here. Yeah, so that's the point here. Again, that actually is the end of the talk. So summing up, probabilistic data structures are awesome. Skip lists in particular, you know, they combine elements from the list types that we all love so much, specifically sorted linked lists and array lists. You know, they are simple, so you understand what's going on. You can easily modify them. They are super efficient, and they are also very robust. And there are lots of other probabilistic data structures, and they are used all over the place. For example, you know, for sorting lists, you have skip lists. For efficient membership tests, you have Bloom filters. For estimating, for example, upper bounds for user messages, you can use things like the count min sketch, and there are many more. One of them would be hyperlog log. I actually thought about including this in the presentation, but it kind of blew my mind and was just too crazy. So I refer to big books for that. And that leaves me just with a final remark. If you're looking for a job in research, I'm actually looking for a PhD student and research assistant. So please apply now and drop me an email. Thanks for your attention, and have a nice football game in a few minutes.